starting the afternoon workshop. Session will run for between now until 14:30. Hopefully you're able to contribute and go along. May I invite the chair, Professor Andrew Starr and Dr. Isidro Durazo Cardenas, to come onto the stage, please. Over to you, Andrew and Isidro.
Good afternoon.
Good afternoon. I must say I'm starting to feel underdressed with both Pavan and Isidro dressed in a tie. Still, at least you know, I'm upright and I've got a jacket on. That's even Mr. Anderson has a tie on as well. I'm very impressed. So, good afternoon, audience. We are going to tell you about some of the railway research going on at Cranfield. So let me share some words and pictures with you. Here we go. So in the next hour and a half, we've got a number of areas that we'd like to share with you, and I'm going to do a broad introduction which will have these topics. We're going to talk about the autonomous inspection systems in 4 different areas: systems engineering, location and navigation, simulation, and payloads. And then we're going to go on to talk about some work we're doing with track and systems, particularly with switches and crossings design, a new project in spot repair of ballast. There's work in cost benefits analysis and prospects for repair with metal 3D printing. So I'm going to first of all invite Rob Anderson from Network Rail to tell us a little bit about the ideas behind the RIRS, Rail Inspection and Repair System, and how that transitions into Remote Inspection and Repair Vehicle, RIMV. Rob, over to you.
Thank you, Andrew. Can you hear me?
Yes.
Good afternoon, everybody. So I'm Rob Anderson. I'm a principal engineer for Network Rail, and I lead the team that looks after specialist remote condition monitoring and the development of autonomous intelligent systems. So first of all, why do we want to move towards the use of robotics in railway maintenance? And prior to the current restrictions on COVID from the pandemic, we have had year-on-year demands from both freight and passenger services to increase the amount of traffic on the network. And because we have a limited network with no ability to expand, the only way to accommodate them is to cut down the time that we have during the night for inspection and maintenance, and thus allowing more time for the traffic to operate. And this is requiring us to revisit the way which we undertake inspection and maintenance. And for several years now, we've been moving towards a greater use of remote condition monitoring. This has been accelerated over the past couple of years and will be during Control Period 6 by the Intelligent Infrastructure Programme. And we are now moving towards the use of or the aim to use autonomous robotic vehicles to carry out this inspection and maintenance. And we've been doing this generally through our work with the Shift to Rail programme and our European partners, primarily through IntoSmart and IntoSmart 2 projects, which we've been working alongside Cranfield University to develop the autonomous command and control architecture. And The command and control architecture, which will be put into various types of robotic vehicle because it's agnostic to the vehicle it sits within, will enable us to undertake the inspection and maintenance tasks without exposing our staff to risk by operating on the infrastructure. It is a very dangerous place to operate, and the use of robotics will bring a greater degree of safety. It will also improve the gauge R&R from inspections. It will improve the ability to control the environment when we're undertaking repairs, and for us to reduce the number of return visits because of failed repairs. So this is what we're aiming to do. Now, we're going to look at the challenges and opportunities. Vast amount of opportunities for us, but the challenges are also huge, not least changing the way we operate to allow the rule book and legislation to let us run autonomous robotic vehicles on the infrastructure, which we currently can't do. But that leads us in now to the opportunities and challenges that we'll have working alongside Cranfield to develop these systems. And I'll pass back now to Professor Starr. Thank you, Andrew.
Thank you, Rob. A great bit of context. So in this image, you see the current selected platform, which is developed from our first attempts back in 2018. And this flow chart block diagram shows the nature of some of the systems engineering behind the driving of the vehicle, but in particular emphasizing that it's doing a job. So we often think of autonomous machines as in the detail of their kind of robotic-like application, but of course there's a good deal of command and control going on here. So that is going to be one of our first themes this afternoon. The nature of our journey is to go from early conceptual research through the technology readiness levels, TRLs, and to move through some of the initial modeling and demonstration. So in the middle at the bottom, you can see our first attempt at physical demonstrator, which is a rail vehicle with a robot on. And that was built in 2018 for some demonstrations of active repair. And now with the Warthog vehicle, we're starting to move up through what I often call baby steps. That is the first steps into complete autonomy. And we have some physical challenges in order to get this vehicle on the railway. And then we need to move it up through its autonomous navigation to get it places, and then to look at the precise task when it gets there. So those move it up through the technology readiness levels, and there is an assessment tool to go with that as well. So when we think about getting around the railway, then we can think that the island of Great Britain is about 1,000 kilometres long, and yet we are concerned about getting to places within a few hundred metres, and then down to a metre, then perhaps identifying some fault locations within a few centimetres, and some of the detection needs to be done within millimetres or even microns. So it's quite a challenge to go through those different types of scale. So navigation is a key issue to be able to get around the place, firstly in the laboratory and then outdoors in a laboratory type environment, but then into a much bigger railway environment. Communications is a problem because in some places communication is great, in other cases it's very poor indeed. Then we need to deal with some of the challenges of the environment, the context that Rob was just describing. Then there's real obstacles, some of which are intended to be there, like overhead electrification masts, and some which are perhaps less intentional but equal obstructions, and that might just be materials which have been deposited near the railway for later use, all of which have a genuine reason to be there, but make a challenge to autonomous vehicles. Then we need to think about all the different information which applies here, and actually getting the vehicle to do its job when it gets there, which is about observation and measurement and action. So we're particularly interested in making the simulation work with the real vehicle. And here you see an image from some of the earlier work done by the Transport Systems Catapult with a different type of vehicle. And really the vehicle itself is something which we are agnostic about. The illustrated example in the screenshot here is a Unimog, Mercedes Unimog vehicle, which clearly is different from the Warthog vehicle. However, it's got a lot of the same stakeholder requirements, command and control issues, systems architecture, and the requirements for inspection, repair, and importantly, verification and validation of that system. So next steps in simulation are to produce a digital twin type architecture in ROS. So those who were on the last session saw some implementations of that in other people's research, and a simultaneous approach that the vehicle can be observed and programmed and be seen to be doing what is in the program in real life as well. Then we're interested in a variety of different payloads. That is involving inspection and repair. So in the first instance, we'll use some simple visible light cameras. The Warthog vehicle already carries 2 as a matter of course. And there's additional sensing like LiDAR, for example, on board. But from an experimental point of view, we've been using thermography in the infrared to detect rail foot defects, and we have also just started a piece of work to look at rail head defects and set up the Warthog with some ultrasonics measurement in order to make those observations. So in the image here you can see some of the thermography work that Isidro's led, and that has positioned an active thermal infrared camera to detect faults on the rail foot. The rail head has plenty of technologies which are quite mature for detecting faults out on the railway, but it remains a challenge to be able to see, for example, corrosion pitting on the rail foot. So I mentioned that we're also doing a number of projects in track work, and within InterTrack we did a project a couple of years ago in InterTrack 1, and all of these either have started or are about to start in InterTrack 2. So we're going to tell you a little bit about our work in switches and crossings, and we've also just started a piece of work on track geometry repair. And track geometry is often dealt with wholesale on a large scale by large track tamping machines and lining machines, but there remains a particular interest in reducing the cost and improving the effectiveness of spot repairs of a few meters of geometry repair. Then we're also looking at some rail defect monitoring with ultrasonics led by Isidro, and that leads into a parallel piece of work with ultrasonic testing on the Warthog vehicle, which has just started as well. So I will stop in a moment. I just wanted to mention that our final example is in repair and cladding, and here you can see an example of where robot wire arc additive manufacture has added material to a tram rail, and repair of tram rails is very important. They're much more difficult to get out of the substrate than the mainline rail, so repair in situ is a big issue. So we'll be telling you a little more about that later on as well. So my time's up. So I will stop sharing there, and I'm going to pass back to Isidro to introduce our next
Thank you,
speaker.
Andrew, and thank you, Rob, for the interesting introductory presentation. As Andrew mentioned, we move on to the presentations by the current researchers on current projects, and they will give you a flavor of what's going on at the moment at Cranfield, and what an overview of the research and what would be potential challenges and opportunities for these different areas of research. So the first, I'll try and share my screen with the order of presentations now. See if that works. Okay, I'm going to go to my. It looks like I'm not able to share my screen.
Isidro, you may want to share the application. So if you go on to the share screen mode, you should have tabs.
Yeah.
Select what you want and then click share.
Yeah, but it's not there, Pawan. So anyway, let's move on. The order I will introduce the presenters anyway after they finish. So the first one is Hao-Chen Liu, and he will be talking about systems engineering. Over to you, Hao-Chen.
Can you hear me?
We can hear you, yes?
Hello?
We can hear you.
Hello? Can you hear me?
Yes.
It seems I have something wrong with my headphones.
Try to go here.
Yes.
Here.
This one?
Yeah.
This one? Oh, I should select. I can't hear my voice. So anyway, I will present, even though I can't hear the sound of audience and other people. Okay, thank you. I will share my screens. Thank you, everybody. Thank you, Andrew. Thank you, Rob, and thank you, Isidro. This part, I will talk about the system engineering for the command and control in the railway remote inspection and repair system, which is RIS system. My name is Hao-Chen Liu. And for the outline of this part, I will talk about the system engineering, the operation concept, and the system architecture, and also the technology readiness level assessment, and also the development and also the verification and validation plan for our for our project. System engineering is an interdisciplinary field of engineering and engineering management that focuses on how to design, integrate, and manage the complex system over the life cycle. And for this part, system engineering, we will use the modified modeling language to design and management our command and control system for the RIS using a a clear path warthog demonstrator, which you can see in the below image. We have a robotic vehicle with multiple onboard sensors on it, to help us to achieve the work acquisition for the inspection and repair. And also we're going to have a track trolley will help the vehicle to run on the track. To design and management, we're gonna start the project. We're gonna start modeling the several parts of the system. They are including operational concept, safety plans, requirements review, TRL gap analysis or assessment, and also system architecture and the VMV plan. For example, the operational concept is to design and the mission faces and the operation motions for the users to understand and guide them to finish the operation. The image shows the state machine or the workflow of the RMRS system, which will start from the pre-motion preparation and then receiving job list from the infrastructure management system, and then by selecting a job, they will autonomously navigation to the job location and position itself on the defect, doing the inspection and the repair, which is the acquisition task. And after that, it will see if there are any other jobs. If there is, it will go to another one. If there are no, they will go back to the workshop and do the recovery to the base. For example, I will show the model diagram we established for the autonomous transit to job part. For example, for this part, it is composed of two parts. One is off-track navigation, which denotes the system will autonomously navigation from the workshop to the track side to a track side position like train crossing, and then by the road rail conversion, it will clap onto the trolley and then it will transit to the on-track motion, and then it will by running on the exact location and do the inspection. With the supporting of the onboard sensor like LiDAR, laser scan, GPS positioning system, and also the environment camera to help the whole system to achieve path planning, path tracking, collision avoidance, and etc. For the project management, our team also established a TRL evaluation tool to help the manager and the collaborators to have a fully understand of the progress and the completion of the project. This project is inherit from the previous one, so for this part, we will start from the TRL 5 to the TRL 7. This tool can help the management to examine the standard of the TRL and the progress we have, the progress in the database by examining each part, by examining each standard criterion of the TRL with the progress or documents in the database. The manager will have a completion percentage of the whole project, and then if if this TRL haven't been achieved, the tool will also give out what kind of skills of the workers or the developers to help the manager to get the help from the people who have these kind of skills. To achieve the command and control of the RIRS demonstrator, we decompose the demands of the stakeholders and the recombination into several sub-work packages, which will help us to build and model a system architecture. For the command and control, we're gonna finish the human machine interface, work acquisition control, and also the geolocation, geomapping part, and also data management, the external system ad hoc interface, and integration layer. Based on above context diagram, we model the system function modules and the information transferring between them using this high-level diagram. Of course, for each of these modules, a detailed model has been established to help the developer to follow. For example, in this high-level diagrams, we have autonomous control system will
How can you be muted?
We've lost your sound, Hao Chan. Isidro, would it be better to move on to our next speaker? Because the
Yes, I think that will be a good choice. So the next presenter is Masumi Rahimi, and she will talk about her work on location.
Good plan, thank you.
To everyone.
Hello. Okay, they have given us.
How can we hear you now? Have you got my
I should stop sharing.
We're just trying to get Mazume going.
Hello. Yes. Can you hear me?
We hear you. Do you hear me?
Yes. Yes. It's clear.
Okay.
Sorry, I don't know what the problem is.
You went on silent. You became muted. So if you'd like to wrap up, then we can move on to location navigation.
Okay. Okay. So.
Okay, may I start?
How can finish, and then Masumi will go on.
Okay, I will finish mine. I have only one slide left.
Yes.
Thank you.
Can you see my screen?
Mazume, can you just wait till Hao Chan finishes?
Sorry for the software problems. For the next part, for the last part, to help us development the system, we're gonna have a detailed development plan, which will use the Gantt chart and also the verification and validation activity plan to first to support our operators to finish the mission phases and also fulfill the stakeholders and system requirements using the checkbox table. This is the below image shows the checkbox table of the requirements. Thank you very much. My part is finished. Thank you. Musume, you can go on.
Yes.
From where I can I click on share screen, but my PowerPoint is not coming to application window. From where I can can you hear me?
We can hear you, yes.
But you know, I click on share screen. I cannot see the PowerPoint in order to share with my audience. From where I can, you know, the first time I saw it, but now I cannot find it.
Okay, is there anyone on the line that can help?
Yeah, yesterday someone faced the same problem during the presentation, and then he refreshed the page with the Control R, then it worked. Maybe
Control R.
Yeah.
Control. No. Just see, I can share this one. I cannot see my PowerPoint. The only item that can on my laptop is this.
Zume, we saw your screen come up, and you were sharing your web browser. If you switch over to your PowerPoint once you're sharing your screen, then we'll see what you're trying to show.
Okay. I don't know. Sorry, I don't know. The only item that I can share is this one.
When you share that screen, we can see your desktop. You need to click on your PowerPoint.
Okay, now you can see my desktop. Yes, this one. Yes, it's coming. Yes. Okay, sorry. Now you can find, yeah? You can see it.
Yes, we can.
Okay, so sorry. Okay, my presentation is about location, navigation, and scale. First of all, about autonomous vehicle. That autonomous vehicle is an agent which is capable of navigating intelligently anywhere. I mean, in various static and dynamic environments, and the application of mobile robots are growing day by day in industry, agriculture, transportation, railway. As far as they are performing complicated tasks that require navigation in complex and dynamic indoor and outdoor environments. They have also proposed a vast variety of positive points to their users, such as increasing workforce safety as well as decreasing their intervention, and also increasing efficiency and quality of the work. But for having an autonomous vehicle, there are four main items that should be met. They are perception, localization, planning, and the control part. In the perception, the vehicle actually utilizes a group of onboard sensors to detect, understand, and interpret the surrounding environment, including static obstacles, dynamic obstacles. In the localization part, robot should find where it is in the environment. In the planning, the vehicle uses the knowledge of the robot's position and obstacles around it to make a decision and plan a trajectory. And lastly, in the control part, based on the selected path, it extracts the necessary values regarding acceleration, brake for the vehicle. In the next part, we have two main type of position acquisition, absolute and the relative position measurement. The first one refers to the localization technique that provides a direct measurements of a global position. And the second one is it refers to the process of determining position relative to a starting point. So for these two methods, different kinds of sensor have been proposed. We have GPS, laser range finder, cameras, beacons, for the absolute measurement, and we have inertial navigation system, that reckoning devices for relative position measurement. And these two type of measurement have some differences in terms of reference requirements, errors. Here I have provided a number of commonly used localization sensor in the industry, GPS, RTK, LIDAR, velodometry, IMU. They have their own pros and cons, and so they are mostly work well for the outside, for the outdoor environment. But for the indoor environment, that we have GPS problem, they have proposed a new technique named SLAM, simultaneously localization mapping. It's an algorithm which actually employs onboard sensors of the robot to construct a map of its surroundings while simultaneously keeping track of an agent's localization within it. As I mentioned, the popularity of SLAM is because of using in indoor places as well as outdoor places are also. We have different type of SLAM, filter-based, optimization-based, that they are including extended Kalman filter, fast SLAM, graph SLAM. And mostly nowadays, three major type of sensor are also applied to the SLAM technique: acoustic sensor, laser rangefinders, and visual sensor. But as I mentioned earlier, these sensors have their own positive and negative points. So in order to overcome to the limitations of individual sensor and improving the efficiency of the overall autonomous vehicle system, sensor fusion method have been proposed. The main challenge in sensor fusion is that these sensors provide us different temporal and spatial resolution, different data format, and also geometric alignment. Here I have also mentioned the impact of having a sensor fusion. For instance, for navigation application, if you use GPS and INS, without fusion, GPS outage, we have GPS outage in denied areas and also drift in INS readings. But with fusion, we have continuous navigation and correction in INS readings. Here also, I have provided a slide regarding the autonomous vehicle that is considered to undertake safe inspection and repair on the railway. So for the localization navigation part, a number of sensors have been considered: DGPF, LIDAR, camera, IMU, odometer. But there are some challenges regarding localization and navigation. First of all, we want a navigation which we want to perform in complex and dynamic indoor and outdoor without human intervention. The second challenge is understanding the environment and context. We want this autonomous vehicle to be able to respond to obstacles, people, and network assets. And the other challenge is resolution, that we expect to have a robot that can detect and monitoring thresholds and defect proximity at least in centimeter levels. So this is the final presentation.
Thank you, Masume.
You're welcome.
So we'll move on to the next presenter, and the next one is Mr. Ram. His work is related to simulation. Miftah, are you there and ready? Thank you. Over to you, Miftah.
Can you see my screen?
Yes, we can.
Yes, we can.
Yeah, sure. So in this project, I will be doing the simulation. So before going to the simulation, I want to share some of our objectives and motivations. So the motivations or the objectives of the simulation is to finding the factors which is involved in the modeling and simulation of an autonomous robot, which will be used in the railway track inspection and maintenance. Then we will try to find the effect of uncertainties such as the vehicle vibration or the location error from for the work of the mobile manipulator. Then we will also review the factors that how the small scale deployment and large scale deployment of the autonomous vehicle actually differentiate. And also we can gain more accuracy. Then we will also examine the effects of the attached manipulator movement on the dynamics of UGV. Because if we want to do some repair work, we will be carrying some payload. So how this payload is going to affect the dynamics of the vehicle. So in these, up to this, it may seem that these all things are actually available. The autonomous vehicles are actually running on the streets, but why we are doing this? The important thing is, remember here, is the accuracy. Because for the repair work or for the inspection work, we need a sometimes centimeter or sometimes millimeter level of accuracy. So this is our main objective. So as we are going, we need a robot which can travel, and also we need an arm. So we choose the Warthog UGV from the ClearPath Robotics and the UR10 arm from the Universal Robot. So we get a mobile manipulator which can travel to a distance and can perform some task or can carry a camera for the inspection work. So the question arises whether it can travel on the railway track or not. So in a sense, it can travel, but it will be not efficient. So our solution can be using a trolley. It's a very simple mechanism which can carry the robot through the railway track. So the robot will be in direct contact with the contact roller. Then the power will be transmitted to the belt drive into the 10-inch railway wheel. So it's a simple mechanism, but effective one. So before going to the simulation, it is important to learn about the joints and degree of freedoms. So when there is arm and UGV, there is total 12 number of joints, 6 from the vehicle and 6 from the manipulator. But when we add the trolley, there is more number of joints. And these more number of joints actually creates a complexity into the simulation. And so we find out whether these joints can be simplified. And interestingly, there are some joints which actually do the same task. Because when the robot and the trolley will be on the railway track, there will be no rotational movement. All the 4 wheels of the robot will actually run on the same speed, and the vehicle will actually go forward or backward, which can be considered as a prismatic joint or the translational movement. So this simplified joints diagram will actually help us to remove some complexities from the simulation, which will actually be faster during the computation work. So we're in a very early stage of simulations. We're using Ubuntu 16.04 and using the ROS Kinetic Game. Then we actually researched about some visualization softwares, such as the VRAP, Gazebo, and then we come up with Gazebo because it will be integrated with the ROS, as we'll be using ROS as our middleware. And for the arm manipulation, we will use move it, and RVs will be used to visualize about the robot, the sensors. So we have started from the baby steps, as Professor Andrew Starr has mentioned in the beginning. In the beginning, we will do the simulation in a lab environment. Then we will go for the track, for the trolley, and the whole simulations. Thank you for your attention.
Thank you, Miftah, for your presentation. Now we will move on from inspection topics to track topics. And the first presenter is Lawrence Tinsley. He will be talking about switches and crossings.
Hello, everyone. Can you hear me?
Yes, we can hear you. I can hear you.
Okay. Okay, can you see my screen?
Yes, we can.
Okay. So my name is Lawrence Tinsley, and I'm working in the rail project with Shifter Rail, working with Andrew Starr and Cristobal Ruiz. And so our objectives are to develop the next develop a design for the next generation of switches and crossings. And so our aims here are to improve the reliability, maintainability, and reduce the overall whole life cycle cost. And this is breaking down into 3 key stages, which involve the literature review in terms of our aims here are to identify what is the industrial requirements and the leading failure modes that affect switches and crossings. And from here, we are engaging with industrial partners to identify what are the existing technologies, the new concepts that are available for integration into a new system design, and new monitoring technologies that will be available for including in the new system. So from this point, we engage with the industrial partners to assign rankings to the requirements so that we can have a weighting for which requirements are the most important, and to rank the failure modes so that we have an assessment of which failure modes are the leading problems for switches and crossings. Once we have identified all of these weightings for these requirements and the failure modes, then we move on to assessing the existing concepts and technologies to find which ones have strengths and weaknesses in these categories, and from there we can identify what the attributes of the final system needs to include. So, for an example, here's a standard layout for an SNC, and there's quite a lot of information. Quite a lot of components to the SNC, and so in order to identify where we are looking to target, we're looking to break it down into the various components that we are actually looking to target. So all of the parts here that are highlighted are the various aspects that we're looking to target. So you have the motor, you have the actuation system, the switch rails, and all of the locations in which we can add sensing and monitoring technology so that we can improve on the detection of the current state of the system and various parameters that are associated with failures. So this is breaking down into the 3 stages. So the first is the literature review on the left, and where we gather all of the information that we require, and we use that to make an assessment of the current technologies, and moving finally later in the project to identify where the strengths and weaknesses are. So if these are our priorities for selecting the new system, we've broken that down into where in the SNC these requirements are actually applied, and this leads us to the design for the concept selection forms, which we apply the rankings and the criteria, and we're selecting against the various concepts. So this is going to result in us completing 6 assessment forms. So we're looking at the existing POE equipment, new concepts, new technologies against both requirements and failure modes. And so this is what the assessment process looks like. So we have the requirements listed with the weighted ranks. And we're rating each of the requirements and their interactions with the different technologies based on the scale from 2 to -2, or 0 with no interaction, so that this allows us to prioritize the concepts that we are selecting. So where we are in the project so far, we've identified the requirements we've identified the requirements and the failure modes, and we have rankings for these requirements, and we're in the process of applying the assessment so that we can identify the design parameters for the new system. And that's the end of my presentation. Any questions?
Thank you, Lawrence. We will move on. I think we will take questions at the end of the presentations. So the next presenter is Kyriakos, and he will talk about sport repair of ballast. No, I don't see Kyriakos in the meeting. Okay, so we can move on then.
Yeah, he was here earlier, but
oh yeah, he is in the list. I can see his name now.
Yeah.
Kyriakos, are you there?
If not, go for the next person.
Yes, the next person would be Lee Kerwood on cost-benefit analysis, but I can't see his name either. And I suppose then we can move to the next presentation. Eloise, are you there? Excellent. Eloise is there. Her presentation is on metal 3D printing prospects. Over to Eloise.
Can you hear me well?
Yes.
Okay, and no. Okay, I think we'll do it this way. You can see my screen well?
Go ahead.
Okay, so I'm just going to talk for a few minutes about wire and arc additive manufacturing. I'm Eloise and I'm working in the welding center here in Cranfield University. So what is one? What is wire and arc additive manufacturing? So it's an additive manufacturing process. So that consists in depositing 3D components, here metallic 3D components, by laying down successive layers of material. We're using an electric arc as a heat source. The advantages is the high efficiency and the cost of this heat source compared to lasers, for instance. And using arc enables us to work in open atmosphere compared to electron beam sources, for instance. We're using wire as raw material, and that enables us to have a very high deposition rate compared to powders. And actually, it's also much easier to handle, easier and safer to handle wire than powder. So using this process, you can see we can deposit in many different parts. Here it's a picture, a slide showing many of our parts that we deposited in Cranfield University. And you have different materials. So we have aluminium parts, top corner left, steels, for example, on the top corner right. And we have all sorts of other materials. Titanium is shown widely here, but we also have copper and refractory metals. So why using wire-based AM? What are the business driver, actually? So what are the business driver for this? So the first one that is often highlighted is the cost saving and the material saving compared to a conventional manufacturing method. So on the corner, on the bottom left here, you can see a titanium landing gear rib. That is normally made by machining a titanium block. So for a part that actually weighs 20 kilograms at the end, you need 240 kilograms of titanium to machine it out of a solid block. But you only need about 50 kg of titanium if you're manufacturing it using one. Given the cost of titanium, that leads to a reduction of about 70% in terms of cost. The other great business driver is the lead time reduction. So you can see an example of the satellite propeller tank here. For a component like this, for space application, the lead time using one can be reduced from years to weeks, and that drops the manufacturing costs significantly as well. The final advantage is here you can use a bespoke geometry for each mission. We can build very large structures, so our largest part, I'm going to go back to this slide, was the 6-meter aluminium component, and you can see the whole team carrying it. I think it was in 2017. So coming back to here, the last advantage is the enabling of new functionality in components. So you can see on the component on the top right corner that we can mix different materials, and we can also deposit some features that can't be deposited or can't be manufactured with conventional processes. So regarding the rail infrastructure, most of our application at the moment is more focused on the aerospace and oil and gas sector, but there's huge potential for this technology to be implemented in the rail sector. The first one is for component manufacture, so replacement of parts that are no longer produced, for instance, and doing so in a very short lead time. Disruptive design, by being able to deposit geometry you can't make at the moment, and functionally graded structure, using expensive material only where you need them. So, for example, using very high grade steels where you need a high wear rate, but you don't have to manufacture the whole part in this very expensive material. The other advantage, which is extremely relevant to this workshop, is the operation on site and track repair. So I know that Andrew showed a picture of one of our tram repair. Unfortunately, I didn't find it. So you can see here an image of TWI work through the Into Track project. So you can actually repair on track and you can use a combination of things, including composite material by adding some powders. So, for example, tungsten carbide to increase the wear rate, to decrease the wear rate of your material. And it has high-grade steels. You can use strain hardening using a machinima pinning, for instance. You can even do localized heat treatment using the heat source you use to deposit the material. And all of this can be done with a robot. Finally, just a small slide on what we are doing now in terms of WAM at Cranfield. So we have a large rolling technology program. This WAM-MAT program aim is to bring this process to a high level of technology readiness. You can see that we have a current rolling value of about £9 million, and we are funded by a lot of different entities, from industry to outside bodies, including the EU or EPSRC and Innovate UK. I put here the link to a new one program, which is our newest research big grant over 5 years. We're working with numerous industrial partners, but also universities. So you can see in the bottom of the slide that we have currently about 60 people in total working on this WAM-MAT program. And if any of you are interested in looking at WAM for a rail application, would be more than happy to consider working on this sector. So just contact me, and we can see what we can work on together. Thank you very much. That's all from me.
Thank you, Eloise. Interesting prospects in there. We have one presentation pending from Kyriakos. Is Kyriakos there? Okay, looks like he's unable to respond. So at this point, I think we can move on. And yes, what we will do now is open the floor for questions first, and then we would like to capture some of the views of the people in the audience with regards opportunities and challenges. We will try to capture this using whiteboard. So I have a couple of questions here from Andrew and from Steve Wilding. I will read those on. Andrew asked, "What are the challenges of running?" Well, I'll let him ask his question, but I will read Steve Wilding one. Apologies if this was covered. I have experienced some connectivity issues. How engaged and receptive have been the various regulatory quality control bodies with respect to these various initiatives?
Thank you, Steve, for that question. And it's something that Rob Anderson and I talk about a lot, because it relates to the first question that I've put in there. What are these challenges of autonomy in a regulated environment? And I think one of the key things is that it's a long game. This is not something which is suddenly going to change in 6 months. It's something that might take 10 years or 20 years or 30 years before all of our ideas will come to fruition. But you notice that there's a lot of debate at the moment about things like driverless cars, and you hear people who are total enthusiasts and they want it tomorrow, and there's those who are much more careful about some simple things like insurance and the legal issues and ethics about what could happen if somebody's injured, for example. So yeah, for the railway applications, we have thought about a number of issues here. So one of those issues is about working with people. So people issues on the railway include that a number of processes that need manual intervention are completely manually driven. There's people on site with materials and tools. So interaction with them is important. So Rob has suggested that there are some good examples from defense battlefield applications where the interaction with people essentially forms a what Rob calls a mechanical donkey type service. That is, the vehicle is present, but it's only there to carry things for people. And then there are systems issues. So, for example, if you drive your car across a level crossing, quite a lot of the aspects of that are automatic. Indeed, the level crossing is part of the road until the railway wants it, and the railway then requests access to it, but that is often done automatically, and for some level crossings it's completely automatic with several loops of interaction. However, where it's not automatic, it's very manual indeed. So, for example, to request permission to take your tractor over a farmer's crossing requires a telephone call to a signalman and a time limit and permissions and temporary blocks on the line are manually put in place. So we started those conversations because we need to understand exactly what should an autonomous vehicle be. And in this particular industry, it might pretend to be a train, or it might pretend to be a vehicle which is not a train, but is operating in a totally reserved situation, which on the railway is called a possession. And working within a possession, it's possible to do all kinds of things with people and machines, but those are not normally automatically requested. We've also talked about the concept of, as you know, most trains make their way along the track from one place to another, but there is also the concept of a pop-up train, which means that it suddenly appears in the track space, and currently such a process is frowned upon, but it's not impossible, and it might be a way of regulating the access. So these short interactions of essentially closing the railway for maintenance or for other interactions are entirely possible today, and they're either done by being a train or by being something that pops up and has a temporary interruption to service. So logically, that is possible in terms of regulation and quality control. But working with people is going to require a lot more cultural change, and there are some interesting ethical points, and I would say that we're at the very beginning of that.
Thank you, Andrew. Is Steve happy with the answer? Does he have any other views from his own experience that he'd like to share with us?
So while Steve's typing, I'll just add that some of the other challenges are associated with some of these cultural issues. One might observe that the railway is quite a unionized organization, and also that there are some cultural divides between those who work vehicles, those who work infrastructure, signaling is different to track, and so on. So those are quite deeply embedded cultural issues. Steve, welcome to the stage.
Hello, Andrew. It's all right, I was going to try and type away, but it's easier to talk. Yeah, your response is pretty much what I sort of expected. I know it's going to be a long game, and I think you hit the nail on the head with that last bit. A lot of it is probably not trust of the technology; it's the culture change that's going to be required. Because, well, straight away, a lot of the resistance to automation, as was said yesterday, is people's concern, the fact that it's going to do them out of a job. And they just need to realize that actually it's just going to change the way they do the job, or what particular job they do. It's not going to make them unemployed. It's just going to change the nature of the work. But it's things, the kind of things I was thinking about was the additive manufacturing. When you make a high quality first level item, how do you then qualify that item? Because you've obviously got a process which in theory is repeatable, but it's a new technology, so you've got to prove that it's repeatable. And the same for your navigation and things like that. When you turn around and talk about identifying a failure on a track to within centimeters, how do you prove that within centimeters is repeatable? And there will always be somebody that wants to understand the false positives, false negatives in your algorithms, etc.
Absolutely right, and the validation and verification of this is again a long game. And you notice that we've used the TRL model to identify some of the steps in that. And quite often we are using some technologies that are already quite mature, but their combination is not at all mature. So that needs a good deal of testing. And whilst there is some practical engineering testing to be done there's also a lot of acceptability and new approaches to rules and safety cases. But this is not impossible. For example, Lawrence is working on this switches and crossings example, and the switches have only got two positions. They only move from A to B and then back from B to A. And yet the measurement of that, the detection and the locking has some mechanisms that are Victorian. And the good point about that is that we understand them quite well. The bad point is that one of the things we understand is how they fail all the time. And they become expensive. They're one of the few moving parts, and they find themselves at one of these interfaces between different parts of an organizational culture, in this case, the signals and track. And it is far from perfect. So therefore, it's really worth addressing because it's one of the most expensive areas in terms of faults, sometimes benign, sometimes catastrophic, but it's certainly expensive in terms of observation, inspection, maintenance, repair, and overhaul. So certainly worth addressing that just technically. Then it's also worth thinking that since a lot of those designs were put down some years ago, in some cases, not just decades ago, but hundreds of years ago, there have been significant changes. So, for example, manganese steel is widely used for the crossing design. So that's the bit where the two rails cross. Basically, they have to accommodate the flanges, and they can be about 8 meters long, perhaps 200 millimeters wide, but they've got a lot of vertical change in the casting, going right down to a base plate where it's fixed to a bearer, going right up to the running surfaces, so that they're a highly stressed component and rescued in terms of longevity by a very expensive alloy steel. But in the days that was perfected, it wasn't possible to have a graded component with a very hard surface and a completely different property in terms of strength below that surface. Similarly, there is some sensing that we can do really very cost effectively today, which only 20 years ago you would have thought was a really expensive thing to do. So there are some distinct areas of technological progress there. But yeah, all of these things will need to be tested. You really wouldn't want modern materials or systems to cause more problems than they're worth. An example I was going to mention of a cultural change is that there is a ball screw drive approved for one of the points operating equipment designs, and instead of having physical clamps for the switch blades, it has brakes on the ball screw. And you can see that logically, in terms of its system design, we might be quite content with that. I've described it as being like a lock on a door, where you might have a deadlock bolt, or you might have a French window type design, which has a multi-point locking design, where the actual motion of the lock is transmitted in, and it's locked logically rather than physically. Some people will go for electronic locks in the future, and whilst you and I might not want an electronic lock on our front door, people who are perhaps disabled and would struggle with keys might really value a logical lock like that. So one has to think about those different approaches to the risk analysis, and risk-based decisions are actually quite well tested.
Thank you, Andrew. So Eloise joined in again the stand. Thank you, Eloise. Just taking Steve's point, how would you describe the technology readiness level that is being achieved for the WAM technology, and whether you've been able to verify the quality of what you do with your process? Can you?
Yes. So. I mean, in terms of technology readiness, we have now a spin-out company, WAM3D, who is manufacturing machines. So we're ready to make parts. For the qualification, it is a challenge. The first thing I'll say is there's no process that is perfectly repeatable, old or new processes. So old processes were qualified at some point. So a new process will be. The question is when. We're working a lot with the aerospace sector, so we have to work hard on our repeatability for this purpose. And actually, our main qualification route rely on a process monitoring. So we're working a lot on process monitoring to ensure the quality of our product. So you won't, if you tell someone, yes, the process is repeatable, they won't believe you. But if you show process monitoring data, images. We're also working on NDT actually with the University of Strathclyde through the new WAM program. So if you can monitor your process properly, it's actually a good route to ensure that it's going to be qualified. So for now, it's qualified part by part, which is a bit painful, but possible. And we're working on the process qualification through process monitoring, and that would enable a much easier qualification process, we believe.
Thank you, Eloise. We have another question by Wael. He's asking whether, he says, in Mifta's presentation, the workhog is mounted on a rolling vehicle. Is that a solution preferred to a single integrated vehicle, seeing that Masume's presentation show the workhog in an open environment?
There's a simple answer to that, which Mifta may like to enlarge on. We did talk about putting railway wheels on the Warthog itself. It's a bit narrower than standard gauge. It's about 4 foot wide, and standard gauge is 4 foot 8.5. And the problem then is that railway wheels would overhang the existing rubber road wheels. And whilst that might look right, in terms of its engineering analysis, it's a bit of a problem because it would put really big moments into the original bearings. Mifta, have you got anything else to add to that?
Yeah, I agree with your points, and I want to add one line, that is, if we add the railway wheel, then it will be difficult for the vehicle to move around into the laboratory environment. It will lose its main purpose, where it can actually run on the plain land and in the railway track.
Thank you, Mifta. Rob?
Yes, one of the reasons that we ended up with the conversion kit rail was the collaboration between IntoTrack and IntoSmart, whereas we originally didn't really bother whether that was mounted on the rails or not, because the command and control system which we're working on is agnostic to the vehicle it sits in, and it was easier for us to have a wheeled vehicle. When I was approached by the guys in IntoTrack and asked if we would collaborate for a proof of concept on autonomous railhead inspection, we decided that we could do with a road rail conversion kit, and it was an MSc project last year for one of the groups, which is now manufactured in the lab. So it's just the circumstances which have led to us having the Warthog mounted on a conversion kit. In reality, the vehicles will be designed to a requirement specification that we work on in collaboration with the guys from Track and any other specialist areas of the Network Rail team. So it's a bit of a stuck together kit at the minute, but it serves its purpose.
Thank you, Rob.
I would add just one thing to that. I'm quite excited about the idea of the Warthog not being on the track as well, because there's things that you can measure while you're sitting on top of the track that are quite easy to reach, like, for example, the rail head. But if you wanted to get a completely sideways view of the track itself, or to look at some of the substructure, the formation that it's built on, or drainage, for example, and the source of a lot of problems is water and drainage, then to be able to get an agile vehicle to get to that location, to get off the track and to have a closer look is something that is quite an interesting idea.
Thank you, Andrew. Do we have any more questions? Please put them in the chat or the Q&A tab. Comments or experiences?
There's one other thing I was going to add about putting railway wheels on the Warthog. Yes, it would put some nasty moments into the system, which it would probably live with for quite a while, but its bearings weren't designed for that. But it won't be apparent to the observers today, but the vehicle is skid steer. So when the two sides of the vehicle are going the same speed, it goes in a straight line, and when they are rotating at a different speed, then of course it turns around a corner. So if we oblige the vehicle to make its track through a trolley, then it still needs to run in a straight line, but it can't put any rotational motion into the trolley itself. The wheels are actually joined together, so essentially it can only run up and down on the trolley. Whereas if the railway wheels were attached to the skid steer system, then it would be possible to put in relatively violent steers into a rail vehicle. And very gentle steer is not necessarily undesirable in tight radii, for example, but it's completely undesirable on straight track and very large radii. So that's something that we've got out of the system, as it were.
Thank you, Andrew. We got 4 minutes left on this session. I invite last question or last comments before we wrap up. From Steve Wilding, from monitoring in particular, are the UK's environmental variations catered for? And if so, how would it be? How do we translate into worldwide deployment?
Environmental variation in this particular platform is catered for in some ways with its already high IP rating in terms of waterproofing and dust proofing and so on. This particular vehicle has already been adapted for defense applications, battlefield applications, and it will wade through relatively deep water. Its body is already sealed for that type of application. Yeah, that's why we're quite interested in being able to investigate relatively wet environments. About accuracy of measurement, yeah, the location information. First of all, GPS is a broad locator, but we're rather aware that the accuracy of GPS is weak in a number of locations. So it's not immediately obvious, but it won't work in tunnels at all. But it won't work in Faraday cages either. So where there are large buildings or clusters of buildings, then the physical location needs a number of different inputs in order to locate the vehicle. Then there are some relative accuracy of measurements to be taken, and that requires thought about how we relate the vehicle to its environment, not just absolute measurements of perhaps an encoder measuring a meter down the line, but also picking up issues like are there other physical objects nearby, like posts, infrastructure like platforms or tunnel mouths. Those are good reference locations. And there are quite a lot of ambient locations, and we've been investigating a new technology that uses video correlation. It's a small company up in Scotland that's been doing video correlation, and they can correlate the images of objects on the track, some of which are deliberate, like clips and joints, and some of which are again ambient, like the patterns of the ballast. And it's very repeatable, as long as it isn't completely moved and refreshed. It's very repeatable and can give sub-millimeter accuracy. And I think for worldwide deployment in other types of applications, that could be very interesting indeed, because it should architecturally deal with this kind of where am I in the world problem, down to about a meter or so, followed by how can I get my accurate and repeatable measurement? And we need a whole architecture for that, which is what Ume is working on.
Thank you, Andrew. And with 1 minute left, I think there isn't much time for questions now. I've managed to take some notes on whiteboard on my own computer, which I look for a way to share with the audience today. Andrew, would you like to say a few words to wrap up the event? I just want to thank you, the presenters, for the big effort towards preparing their materials to this event. Thank you, the audience. Andrew, over to you.
Yeah, absolutely. So you've taken the words out of my mouth. I think perhaps in closing, I would say the real challenge here is that this is a big system challenge. Sometimes you look at the individual ingredients and you think, oh, that bit is mature or quite easy to do. or its challenges are minor, but to put them all together and to stitch them into higher TRL development, you soon see that there's lots of challenges for demonstration. But thanks very much for your questions. They've been stimulating, and thanks for everybody else for paying attention to us. We appreciate it.
Thank you, Rob. Pavan, would you like to come on?
Very much for the session. Quite an interesting chat with some real world challenges happening and how we facilitate them as we progress into a future where we are all stuck in front of technology-based solutions. So thank you for this, for all those who are attending. We will briefly go back to the floor and we will go back into presentation mode in just 5 minutes before the next session. The next session starts at 14:45. We've got 3 parallel sessions. I will post the links for the parallel academic sessions, session 7 and 8, which will be in rooms 1 and 2. And there is also an industry workshop which is happening in the auditorium. So please do join us, and we will see you shortly. Thank you, everyone.